Okay, today we're going to start with waves. This is the most important part of Unit 8. Up until this point, we've been just doing preliminary stuff to make sure you guys were okay with oscillations and sine curves. We're not going to go too far today, but I do want to first start by looking at where we've been so far in this unit. So we had pendulums. We had the pendulum oscillate back and forth near our pocket lab. We saw it trace out a sine curve. We saw the important parts of the sine curve were the amplitude, the phase shift, the vertical shift, and then the most important thing was the frequency, how quickly it oscillated back and forth. We saw that the frequency and the period were determined by the length and the planet that the pendulum was operating on. Then we looked at oscillations on springs, and they also created sine curves. They went by the exact same equation, and this time the oscillation of the object on the spring depended on its mass and the spring constant of the spring. So this is all we've covered so far, simple oscillations with the main goal of getting you to understand these sine curves. Now we'd like to take it a step farther and hit the meat and potatoes of this unit, which is waves, with the idea of learning about sound and light, two very important things in our universe. Okay, so I want to start out by making sure you guys understand what a wave is and what a wave is not. So a wave, by definition, is the propagation of a disturbance through space and time. Let me explain what that means. To start a wave in this water, we need to drop something into the water. That's our disturbance. Waves start with a disturbance. That disturbance does not stay localized like a pendulum or a spring, but propagates, travels outward in all directions. So the disturbance propagates through space and time. So you see we drop the object in, you can see the ripples propagating outward. Those ripples are what we call our wave. A wave is also a transfer of energy without a transfer of matter. It's a transfer of energy, not a transfer of matter. So to show you this in another sense, let's take a look at these battle ropes. And the disturbance is going to be this athlete's hand. She's going to move her hands up and down. That is the disturbance. You will watch that disturbance not stay here, but propagate through space and time.
Let's go, Daniel. Oh, great job. Lean back just a little bit. Good. Great.
Okay, so you can see how the disturbance travels outward through space and time. That is what we call a wave. Notice the energy from her hand transfers through the rope, but no actual matter leaves her hand. It is only energy that is traveling through the rope. Propagation of a disturbance through space and time. Transfer of energy, not a transfer of matter. Okay, and when we take a look at our wave, you'll notice it looks like a sine curve. But it's unlike a normal sine curve in that it doesn't stay in this location, but the rope moves up and down. The sine curve moves left to right or vice versa. So it's a sine curve that is in constant flux, constant change. When you take a picture, you can see the sine curve, but over time, it's constantly changing. I want to make sure you understand what is a wave and what's not a wave. We oftentimes think of waves down the shore. And when you're way out in the ocean, these are legitimately called waves. And when you watch, you'll notice how the people bob up and down, but don't actually go anywhere. Because all that happened was a disturbance traveled through them. Energy only traveled by them. When you look closer to shore, even though we call these waves, these are technically not waves. These are breakers. Gravity is collapsing the wave and causing the particles to actually move. This can move something forward. Okay? So when you think waves, don't think of the breakers down the shore, but think of beyond the breakers where you have a transfer of energy but not matter. Here's another way to think of a wave. Think of it as composed of a whole bunch of little masses on springs. So when you saw that athlete moving her hand up and down, and we saw the wave propagating through the rope, each part was oscillating just like an object on a spring, but each part was oscillating at a different moment in time. So it would look something like this. If you focus on just one spot, it'll oscillate up and down just like we saw before. But if you take a picture of it at any time, each spot is going to be in a new location, and it's going to create a sine curve, both in time and in space. So our equation is going to look a little different than you're used to. It's saying position as a function of horizontal location and time. This equation will tell us what's the y position of each spot based on how much time has gone by, and also how far we are along the x-axis. So we have familiar things like amplitude. We have familiar things like vertical shift. But now we have time and x as two separate variables. Time is going by, and there's lots of different x positions. So it's a little bit more confusing, and hopefully this is our main thing today, is picking up on how to work with this equation. Okay, so again, here is a different example where we actually see it traced out on Desmos. And again, what this is saying is, what is the height of the wave at a certain x location and a certain moment in time? So time and x are the numbers that you're going to be changing from moment to moment. The A, the B, the C, and the D, they will remain constant as time progresses and the wave moves along. Okay? So you have two things happening at the same time. This picture is showing horizontal position and vertical position. And when you have something like that, this old familiar from here to here, which used to be the period, is no longer time. The x-axis is no longer time, it's position. So what this represents is what's called wavelength. It's how long it is from one part of the wave to the next time you get to that same part of the wave. How long is the wave? It's called your wavelength. It's horizontal position on the x-axis, and then you can see what your wavelength actually is. Okay, you can see it as the wave travels. The sine curve is going to move from place to place. You notice how the particles are simply moving up and down as the energy passes by. All right? So that's how it's different. Our sine curves are now in motion. Okay, so your numbers are going to look something like this. Again, the 3 represents the amplitude of the wave. The 5 represents how far it is to the middle of the wave. So you could see 5. You could see 3. Okay? These two numbers now take on a new significance. This number, the one in front of time, will tell us the frequency. And as we saw before, this number represents 2 pi times your frequency. So if you know that number, you could figure out the frequency. How many times will the thing oscillate per second? This number is going to tell you the wavelength. And this time what you do is you get that number, you put 2 pi, and you solve for the wavelength. And again, the wavelength is the distance from peak to peak when you're looking at horizontal position. Okay, so when you get a graph, the first thing you have to do is when you look at it, horizontal position, that's on the X. So this is wavelength. Again, you could have measured it from the bottom. You could measure it from the middle. It doesn't matter. Just similar spot to similar spot, wavelength, and that is usually in meters. In this case, it's in centimeters, so you might have to convert. If, on the other hand, you get a graph and time is on the x-axis, then the distance from peak to peak is not the wavelength, it's what we're used to, the period. Okay, the time it takes for one complete cycle. So you have to look at your x-axis, and that will inform you of what your sine curve is like. It doesn't matter what's on the x-axis when you're determining the d and the amplitude. Okay, I actually don't want to go any farther today. We'll be coming up in a few days. We'll be learning about sound waves, light waves, and all that. I just want to test and make sure the things I told you today made sense. So I'm going to ask you to complete some things on a Google form to make sure you understood what we just talked about.